Good morning, good evening, good afternoon, depending on where you're joining us in the world today. We're broadcasting live at MIT.nano. In particular, we're in the Immersion Lab. The Immersion Lab is a central facility engaged with helping you, MIT users, off-campus users, leverage the powers of immersion, the powers and tools of gaming to advance science, to advance engineering, to advance education. So I invite you, we're here today virtually and physically, some of us, but I invite you to come knock on our doors, send us an email, reach out to understand how we can help you apply the tools and the language of gaming, ambient physiological monitoring, novel displays, novel technologies to really think about the new ways that we can move the needle forward together. So today, we're here to celebrate how we can think about the novel ways of using augmented reality to manage and explore infrastructure. We know how to use the wheel. We're still developing the ways that we're going to use augmented reality. So Arman today is going to share with you some very innovative and novel approaches to thinking about how we see behind the walls, how we engage with our physical through the virtual. Again, enjoy, ask questions, and I'll turn it over to Arman and take it away.
All right, my name is Arman, and I'm a graduate student, second year master's in system design and management program. And I'm also working on research, how can we use augmented reality to improve operational and maintenance tasks. And just a little bit about my background and how it motivated me on working on this project and exploring. Oh, louder? Okay, sorry. Can you hear me? Is good? Okay. Right. So I was working in oil and gas before coming to MIT. And so the way that my work was involved is around developing and building models. How can we represent the systems that we were dealing with, like hydrocarbon reservoirs, the subsurface systems, and how can we use those models to maximize and optimize production? That was my main work involvement around the building and optimizing the infrastructure of the system. And one of the interesting things that I encountered when we were dealing with different aspects of our work was when we were dealing with our system, we were modeling the complex reservoirs, and we most of them are, you cannot really see them physically because they are located like 1,000 meters under the ground, and we had different groups that were dealing with the same type of system, but from the surface level. So we had different viewpoints on how we were applying our approaches on how we can use our techniques to operate that system. So I've seen when we were doing the field visits to one of those like well sites, I've seen the issue that there was some level of differences when we were talking about how can we operate the system, and we were speaking with field operator and engineering department, for example, and we had different mental model how we think about the system. So when we thinking about the model, so we would see on the right side that this is how we view the this representation of the field or the gathering system or the well side, the flow lines. That's how we would be operating the field. And when we are talking to the field operator, from their point of view, they don't have that understanding what's under the surface. So their only focus is about looking at the number of valves, number of pipes, which pipe should be switched on and off, and which valve should be turned. And that's where you had that difference. So when that's where I was thinking about how can we link that gap between communication of having the virtual and digital model be integrated with the physical systems. And that's how I started to explore how can we use augmented reality as a tool to link that gap in the communication and in the representation of physical and virtual systems. So now that's where I started working on developing a concept for around the MIT.nano. So what is a nano AR? Nano AR is a digital representation of the system of the MIT.nano facility. And for those who are not familiar, on the call, maybe MIT.nano is a research facility that's focused on research around advanced technology and advanced materials and nanotechnologies. And it has multiple facilities inside that building that we can take as our potential concept to develop the model that we can operate and test and see and gather the feedback and learn something from it. For example, it has on the subfab area, there is a characterization room. There are clean rooms on the multiple floors. There's a fan deck that provides the equipment to filter and remove the particles from the air in the clean rooms. And also there's a prototyping room. So we have a lot of material to play around with, and we had a really good amount of data that we could collect and build a model around the facility. That's where it led us to think about, okay, so we have this data, we have the models, like building information model of the system of MIT.nano. How can we use this model and develop a concept that we can test around and build an experience that the user can interact with through augmented reality? And that concept, the first concept that led to us to explore, okay, let's focus on the operational and maintenance tasks. So let's think about what could be an interesting approach, how operator who would be managing and operating the certain aspects of the building, with certain like facilities of the building, like fan deck, for example, to operate the valves and switches to support the environment in the clean rooms. What would be useful for them to have in the AR application or in that AR experience? So we started focusing and narrowing it down to augmenting the engineering infrastructure, and that's where we started looking for the data or the assets that we can collect from those BIM models to only represent filtration system, like fire safety. It could be piping, and plumbing or ducts. So things that usually you wouldn't see around the space when you're inside the room. So when you're in the room, you definitely you see walls and furniture, but things that are behind the scenes, like behind the walls, ceilings, and you wouldn't notice them. So that's where we thought, okay, maybe that will be useful to test and see how can we augment that and overlay on top of the physical systems here. So that's where we proceeded. That's how I proceeded further with development. But before building the actual scene, I just wanted to highlight some of the constraints that we had in developing this experience. Now, so the constraints that we should keep in mind of when developing AR experience or any game development application, any game development has this constraints that are like two opposing forces that are pulling the performance of the game or the performance of the AR or VR simulation into different sides. So you have graphics quality, you have the textures and the materials. So how realistic all the objects look in that game or in that simulation. That's like one side of this boundary of this envelope, and the other side of that constraint is the game performance. So how smooth you want the system to operate when you interact with the simulation. So those are two things that you need to keep in mind, and you need to find the balance really by applying certain features, by changing the texture, by removing number of polygons. So that's where it's more art than science, really, when you find that balance, because it could be different case by case. So that's where it requires several iterations to find that the sweet spot between these two constraints. For the applications that we will apply for development, so we're heavily dependent on the Unity. So we'll be using Unity for most of our feature adjustments and how we set up the interaction between the user, the AR player, and the actual system. So in our case, MIT.nano augmented overlay. That's where we would be developing and adding interactions. we would be using also Blender for changing the textures and the materials and removing the that level of detail that will hinder our performance. So that's where we want to play around a little bit with the quality of our objects and our assets. Autodesk is something that we use to just to grab our initial source file. So Autodesk or any AutoCAD design platforms we can use. It's really for us. It wasn't a big difference which source file we could use, but we needed this 3D designs to start with because we're using building information models. So that's how the MIT initially built. So we use that as our initial first step, and we are also relying on MetaQuest headsets and Meta SDKs to develop interactions and Quest Pro and Quest 3 was our choice for the hardware for the headset. The reason is because we want to have the pass-through feature. The pass-through, just for those who are not familiar, in the VR and the AR, you have this capability to see, like to see what surrounds you in the space, so you can walk in the headset without taking them off. That's the pass-through or see-through. You can choose either one. But the difference between those two is that see-through is essentially it's a glass, and you can look through the glass and see the holograms that are displayed through the waveguides. Versus the pass-through is where you just look at the display, and the headset using the camera to show you the visual of what you're seeing around you. So you're not really looking through the headset; you're just looking at the display inside the headset. That's the main difference. Yeah. So first start with the data collection. So we had this massive file for MIT.nano BIM file in Autodesk Navisworks, and that's where we wanted to first think about. So if you think about the concept, you want to know, okay, how do you want to organize? How do you want to start building this project? How do you want to split the facility? Do you want to do this by room or by a floor level? There are many different ways. So that's where you need to be decomposing this large piece into smaller parts and smaller sections. That's where it will be much easier for your further development. So you need to think about these things one step ahead. And but really, it also might require some iterations. But this is where we would start collecting our data. You can also import additional assets. If you need something is not being built, you can develop yourself, and you can introduce to the AutoCAD design, or you can just import them into the Blender or Unity. It's a matter of what assets do you need, or what objects do you need inside that build, inside that experience. So that was our first initial step. Yeah, it's pretty much saying same thing, except that if you think about what do you need everything in that model? Probably not. If you look at one of the examples down there, like you wouldn't need to import walls, for example. That's where we're not interested in displaying everything that's visual. So you don't want to see the actual like furniture, right? For example, we want to only focus on the engineering infrastructure behind the walls and the facilities. So that's where our focus mainly led to take those objects. Now, the next step in this process is pre-processing of the original files. So that's once you import the files from Autodesk or from AutoCAD, that's how you would see them in the Blender, in our case. And definitely, there's a lot of material that you wouldn't need in your design in your AR simulation. So you would want to start thinking about how can you make this model simpler. There are several things you can do, and there are many other sources that you can search for. How can you remove number of polys? How can you make the model much simpler? In our case, this is what you probably would be looking for. This is how we represent our system. So it's mostly pipes and infrastructure. And so first of all, once you import your objects from AutoCAD, you will see a lot of different small pieces bundled together. So you want to first thing you will want to do is to cluster all of those smaller objects into bigger components, because that way you can save computational resources, because it's much easier to process less number of components versus the large number of components, and that's where you would want to kind of group them and cluster. And also the next step would be to remove number of polys, do some decimate function. Like there's some techniques that you can do in Blender to remove that extra level of detail that you wouldn't need really for your AR experience. So the main thing that really helps us to move faster is just to focus on clustering objects, removing some number of polygons, and also material. Yeah, you wouldn't need to have the material that are imported from AutoCAD. You can add the materials that are much simpler from Unity, and that was our approach that helped us down the road. Now for the development part, this is the fun part. This is where you introduce all the features. This is where you decide pretty much this is where you can design your interaction, how you or like how AR player is interacting with the system. And Unity is a very useful tool. It has a lot of open source packages that you can apply, and even with low level of like or low skills, I mean, inexperienced programmer can learn this really fast. There's many resources, and right now, especially with Gen AI tools, you can script any functionality relatively easy and fast, because there are many things that are not independent. So once you create a script, you can just drag and drop that component into the object, and it should do the work. And yeah, so the first, when you start the Unity project, you want to make sure you're setting up it in the right way. You have the right platform. In our case, it was Android for Meta Quest devices, headsets. Yeah, so we were focusing on Quest 3 and Quest Pro mostly, pass through on. We needed some hand tracking, so we want to make sure that the experience was as natural as possible. So there wouldn't be a need to carry the controllers in the hand. So you would have to just use your hands to navigate or switch the do some buttons control, or yeah, do like basic stuff with your own hands. And that's where these headsets have the function to track your hands. And also thinking about the setup for the camera. So the level setup, is it eye level? Is it floor level? For floor level, it's when it's grounded to the level of your of the floor, or your feet. That's where you probably would think about having furniture designed to that level. But in our case, everything was actually overlaid on top of us. So it's mostly we're at the eye level of the elevation, so we wouldn't need to have floor level. But things like that, you just want to think about when you set up the project. And there's multiple SDKs from Meta XR that we also introduced to have that interaction with hand tracking and other components as well. I just want to go through like some basic things that we need to have as a minimum to have that smooth interaction. First one is rigid body. So this is where you want to think about the physics of the objects. And rigid body is the physics component of Unity, where you can remove gravity or you can add gravity. You can make the objects static so they can freeze in the location. And in our case, that was essential because we wouldn't want to have any facility. We wanted them to be anchored to a certain spot and to a certain location, and that's where we would have those components introduced. And yeah, we would need the gravity. So the main, I guess, feature that we had to have from the rigid body is the collision effect. So if we're grabbing some objects, that's where you need to have that collision detection. And collision detection is actually triggered by box collider. I'll explain it later. But this is things that you also would need to have for most of your builds if you're developing AR experience. Yeah, and the box collider is actually showing the shape of that or dimensions of the object. Yeah, in our case, I had to put like box collider around each room. So if you walk around the building, you would see like it will have to have some sort of a indicator or the area where once you enter that area or that box collider, it will trigger an event. So that event could be anything, could be activation of the assets, so you can make them visible or invisible once you walk between the room. So that's just this basic stuff that help you down the road when you're scripting and when you're adding additional functionalities. Yeah, and then that's where you toggle those, like put all those together, the box collider and the player. So the player essentially is your camera of your center eye anchor that you could assign as a moving collider. So once your collider, which is around your headset, is enter another box collider of this room, for example, it will activate everything around you, and then it will deactivate everything that's in other colliders. That's like just basic stuff that you'd have to script and add those components in the Unity as a separate component. And then we also like I thought, what if we just add some controls to the user? If an operator walks around the facility in an AR headset, maybe there is a need for him to have some level of control, what he wants to see, what he or she doesn't want to see in the view. So introducing buttons to switch on and off things would probably make sense in this simulation. And good for us, there's already a built-in functions from Meta XR SDKs that we can just grab one of those buttons and introduce. And in our case, we attach those buttons to the hand, to the palm. So when you look, like, you have to like stare at your palm, and it will show the buttons, and you can interact with that menu, I would say. And it wouldn't show up all the time in front of you. So that's another feature that another functionality that you can play around with. Yeah, and also you also need to script the what it does, what each button actually activates when you press on that button. Like on click, you have to put a tag for a certain asset. And that's like when you put the button, when you press a button, it will activate those tags with those assets that are assigned to this tag. It's just some basic stuff, and certainly feel free to use the benefits of having Gen AI tools like GPT to help you down the road with the scripting. It makes things much faster now. And yeah, one of the last steps to make sure that the simulation is as natural as possible is the calibration and scaling. Once you put the headset, you want to make sure that the dimensions are in place. And for example, in our case, we wanted to match the like the virtual points of the fire sprinklers that are matched with the actual ones in the space. So those reference points, as I would call them, are critical in making sure that your physical and virtual aligns physically. So that's what could be the tricky part, because in our case, it just turned out that the actual model was not up to date, so it was hard to match. And then we realized that we probably shouldn't be spending time on matching the not up to date model. So you want to make sure that the model is up to date, and it should follow. And that way it will be much easier to match the virtual model with the actual asset and facility. So it could require some back and forth between calibration and testing. Yeah, let's just see some demos. So this one, it will show you how the interaction will actually activate once the player in the AR headset will walk around the room. And yeah, so this is how the field of view looks, and how so actually this one has a built-in function in Unity that helps activate those assets, not by the box collider that I was describing, but actually automatically setting up the distance. If you want to have a certain distance where the objects will be activating. That's how it will look in the simulation. Oh yeah, sir. Sorry. So in this space, we in this view we have two types of assets. So we have the red ones. The red pipes are the fire safety system. So all the fire sprinklers. That's where the water would come to the for that. That's basically it's it will be like behind these walls, on the top, and the green ones are the ventilation systems, the HVAC. So that's where the filtration and the fans are located. So I'll show you in the next video that we're gonna do the walk around and with the headset, and it should show the how it looks beyond this room. Yeah, just also testing some other small features, like we can add some distance, like we can add the target. For example, if we want to have operator know where he needs to go for a certain task, we will add a target object, and then we can add some simple navigation like you would see in the game, like this navigation arrow, which is very simpler approach, but there are many other ways that you can go around this. You can be creative when you design these features. Yeah, and then we tested some buttons control. We introduced things that we can add some components. For example, we were thinking about some troubleshooting exercise. If an operator went to a facility and he needed some do some potential troubleshooting with additional tools that he doesn't have, or he needs to match some certain design or dimensions of the tool with the facility. So he would press a button and he would try them out at the location. This simple things that you can also try, but this is just a testing of how buttons would interact. And the last one, this one is the walk around around the corner of the of this floor. So so you would want, so that's where, so this is now it's overlaying at a larger distance everything that you would see, um that you would not see, but you would see this through the AR headset. So it's kind of like having this X-ray vision of the building. And this is just also one of the testing. It was in the process of the testing. So some of the elevation might be not up to the right elevation, but it was just to show how the process of calibration and testing looks when we're developing these type of simulation. Right. So now we went back to the initial point, and everything stayed in the same place. So it's anchored, but sometimes when you go around the corner, you might see some misalignment. That's the thing about having making sure that the scaling is right, and it requires several iteration and testing. So but overall the scaling in Unity, the 1 unit measure is equal to 1 meter, but it could be off sometimes. So you want to maybe add additional multiplication to adjust for that factor. So there could be some inconsistencies between the model. So now we have this concept. So we develop this workflow. So how can we investigate and answer the research question? Does the AR actually help us improve the task on the job? And things that we want to measure are task completion times, number of errors or number of mistakes, and if there's any reduction in the cognitive load. These types of measurements or metrics and figures of merit are typical for running a study with the task completion, and also based on the literature review. It's a typical type that you would measure during the like experiment or a study. So we will be using the same headset, the hardware of Meta Quest Pro or Quest 3, and we have several concepts to choose from. And the thing that we would want to choose the concept that would require you to also compare the like a treatment group for using the headset and the conventional way of doing some task without the headset, and that's where the key difference would show up. And yeah, so I'll explain how we chose our concept for the AR study. So this is the workflow that I just went through. Yeah, so now we can choose. This workflow is pretty robust. You can choose any facility equipment. You can overlay and run the experiment with different objects now, and it worked actually pretty well with the so we had uh, a file that we received from one of the companies that did the scanning of this building. So there was a third-party contractor who did the scanning, and we were able to take those files of the new I guess of the area that's in the basement of the subfab area, and we're able to run through all these steps and test I mean within the couple of days or even the weeks, just to show that this process is pretty I guess it works well with any types of complexity or any types of objects that you can introduce in addition to what we explored for the nano AR. So that's where we proceeded to work on the next object, which is this FRED device, which is fiber extrusion device. It's a desktop tool to learn and teach how the fiber extrusion system works, and to help educate and teach how the principles of manufacturing and advanced controls and also data acquisition. So we had this AutoCAD design, which was really good for us. And actually, in this case, we didn't have the Autodesk, the AutoCAD files. We just had the Onshape, which is the cloud-based platform for AutoCAD designs. And you could see that the files are pretty high in level of detail, which we might not need to have for the study. And once we start working on that on the pre-processing part, definitely we want to have them these objects in a much simpler less detailed level than we would have them in AutoCAD design. So this one, comparing to the AutoCAD, now it looks as a more simpler version that should be fit for purpose for us. In our case, for the study, it should have more or less same representation. Nothing is much different. And yeah, then you add it to the Unity development engine and add the features, add the buttons, interactions, and then you go and test and calibrate same way that we did with a Nano AR. So this right now we're just doing the calibration manually, just aligning how the object will fit the physical one and the virtual one. But we're also testing some other techniques like anchoring, and that's where we're still kind of in the learning process of doing this in a more precise way. But for us, it worked well just to, because since it's a very simple tool, and it's relatively easy just to do it manually and much faster. But for a complex system, you might need to have some level of automated approach or some control to apply anchors and rescaling techniques. Yeah, and this one is just testing the interaction with subcomponents. So we tested the guide system to guide the operator to show where to put the objects or how to assemble this device. So that was part of our another testing step. And then now that we have this interaction in operation, we can go and run the study and collect more data. So in this case, we are showing the virtual components overlaid on the real Fred device, and we're measuring how fast can we assemble compared to the groups that are not using the AR headset. So this is the just example of how it can be used for your study. Yeah. And with that, I think that should be all for my part. And we just started the study, so we're running this. This is actually the pilot, and we're testing how human subjects are interacting with the system and with the physical, and if there's any obstruction that we need to keep in mind of. But so yeah, we just the first step was just to make sure that it's the AR model is working and is functioning. But based on the research that we did on the literature review, yeah, it shows that this could be promising for in general, on average, AR can help reduce the task completion time. In some papers, it shows that it could be by half, like 50% of the time. And for number of errors, it also helped reduce number of errors that are made during the job. And the cognitive load, which is the assessment done by the NASA TLX assessment, and that also showed that the results can show that it will help reduce that cognitive load. And we want to prove that if we have the same results in our case.
All right, Arman, thank you so much. And so we're going to take some questions. We're going to leave a little bit of time. Kelly went ahead and submitted that in chat. So if any of you guys online have any questions or comments, feel free to put that in chat, or if anyone here, yeah, feel free. Yeah, so he said, given the complexity of all the steps within this system, is there any automation that we can do to kind of expedite maybe changes that happen in the future?
Yeah, that's a good question. Actually, I've been looking at this process first by establishing what steps are required to do manually, so then we can at least find the bottleneck in this workflow. At this point, if the design changes, I mean, the fastest way is really importing objects into the. I mean, any change that is made, we just grab those change and bring it to the Blender, and that's where we will add that prefab, that section, to our simulation. But how to make it automated? That's a good question. I don't have an answer on automation part right now, but I think it's something to explore and improve on making it more efficient.
And we have a question here regarding the second project, so the Fred project. Is it easy to understand the system with many components removed? I wonder what kind of components they're referring to in that question.
Mm-hmm. Yeah, I mean, if we remove walls and things like that,
Mm-hmm.
yeah, I feel like when you're walking around the facility, you have general idea if the objects that are overlaid, where the calibration is the key. You want to make sure that the dimension and the scaling is up to is as precise as possible, because once you remove them, that's where it can get distorted, and if it's distorted, then it doesn't make sense to look at the objects that are like standing somewhere in the wrong spot. So if you have a calibration done right, it should intuitively tell your brain, I guess, process that information as naturally as possible. That okay, if there's a wall, and behind the wall there's a certain piping, that's where you would expect to see if you tear that wall apart, right? And that's how like our understanding was, that we only need the features that are not really visible to our eye. So and calibration would help us avoid any inconsistencies. And yeah, so that's how we are approach.
Yeah, and that actually does allude to this next question. How did you ensure the correct placement of the AR component in the real world? So kind of that overlay. And I know we kind of talked about strategies on how to go about doing this.
Yeah, like finding the right spot, right?
Yeah, so this would be kind of the calibrating.
Yeah, like the reference points. So
Right.
anything that you would see in the virtual object that are kind of sticking out of the walls, like one of the example was fire sprinklers and or the HVAC, like the fans and the something that you would see physically, and you would want to anchor those objects around those reference points. That was our strategy that we chose. But definitely we can introduce additional things that we because it's our design, right? So we can add things that are actually in the room, and we can anchor how we can initiate the simulation around that, like the virtual space. Like for example, if we're standing here, we can overlay like one of these cameras, right? And we want to have to initiate the game when we are standing in the middle of this room, and that's how we can introduce that anchoring effect, and we can match the dimensions of this, like for example, of these cameras around here. So that's kind of just example how can you go around this on finding the right spot and finding the right placement of virtual objects compared to the physical ones. Yeah.
Thanks. Great questions. Keep them coming. Is it possible to combine the physical property other than shape of an object into the AR system? So perhaps material or texture. Might be. So I think you might be referring to haptics in that.
Physical property other than physical properties.
Maybe. Yeah, sure. Mm.
Yeah, for that we'll need more data, and if there's a real time. Yeah, for the question, can we actually see if there's any like a pressure or temperature or some sort of a like measurement behind the actual behind the virtual representation of the system? So yeah, for that we'll definitely need more data. We'll need more data acquisition linked to the actual system. But right now it's all I would say not live. It's more static. So once we build it, it's the file just being sent to the headset, and we don't have that feedback, like the real-time feedback loop that you would call that you would expect from the digital twin, right? So that's where digital twin kind of comes into play. So we want to have that real-time interaction, and that will be a little bit heavier to process that information because you need to have some level of control, and we will need to connect the headset to a cloud, and then where we can build those like take the measurements, acquire the data, and also overlay in real time. I think that's interesting thing to test, but at this moment we only have a static version of the building.
It'd be a great use case though.
Yeah.
Seeing some real-time data coming
Oh
through.
yeah, definitely.
Yeah. All right. And anybody else? I know we Arman kind of threw a lot at you guys, talking everything about the development and jumping into Unity. And have you used Unity before jumping into this project?
Yeah, that's the thing that and I haven't used Unity in my life before, and this is where I felt that the learning this process from scratch was helped me find I guess the bottlenecks or things in the process where we can help improve and focus on the right steps to get the model built as like fit for purpose, right? So we don't spend too much time on developing things that we don't need for the experience. Yeah, but and actually we tested on us students that we just joined this semester. So we have this workflow, and we introduced them to this new like way of building this experience, and they were able to catch this really fast. So I think now it's becoming a really powerful tool to introduce this to new students, and they can learn and develop this in a much faster and efficient way.
Yeah. And it's just working with VR and AR as a headset, and all of, with all of the complications and limitations that you have on that. Because I like what you mentioned early on, kind of balancing both the technical and how we can get kind of utility out of this, but also you know, the artistic side. So figuring out what kind of changes you need to do with the assets, but still being able to convey that information and sustain the performance on the headset, because this has to be standalone, right?
Right.
You do have to walk around. So I just thought that was a incredible journey that you kind of took us on. And then you're asking, is this useful, right? Jumping into that research side of things. So definitely stay tuned, everybody else, to see what the outcomes on that project is. But in the meantime, I think that does bring us down to our hour. So if anybody does have any kind of continued questions, you can shoot us an email at immersion@mit.edu. That comes right to us. But we will be back in 2025. We don't have anything anticipated for the December for our Immerse series. So stay tuned for early January. And thank you all for joining us today. Thanks, Arman.
Thank you.